So the next section we're going to look at here is what's called a library of functions, and we've been spending a lot of time talking about, in terms of graphs of functions that are linear. And one of the things that we're going to look at next is some other types of functions, particularly those that involve some different things with curves, parabolas and cubics and things of that like. So a couple things here first, just kind of talking about anytime we introduce a new function, we're going to look at some of the characteristics of those functions. So let's first just talk about some different things that involve what's known as a linear function, because a line is a linear function, assuming that, once again, we're kind of getting back into this y equals mx plus b type form. So some of the characteristics of a linear function. First of all, the domain is the set of all real numbers. The domain goes from negative infinity to positive infinity. The range of the function is also the set of all real numbers. So once again, the range goes from negative infinity to positive infinity. The graph has one intercept, and that's at 0b. And the graph is increasing, meaning it's moving in an upwards direction as we read it from left to right. If the slope is positive, it's decreasing from left to right if the slope is negative, and it's constant if the slope equals 0. So just some characteristics there that involve a linear function. So one of the examples that we have here is it says write the linear function f for which f of 1 equals 3 and f of 4 equals 0. So what they're giving you when it gives you this type of form as far as being able to write a linear function is it's giving you 2 points on the graph. So this right here would be the point 1 comma 3. This right here would be the point 4 comma 0. So just remember, when we're talking about writing the equation of a line, writing the equation for a linear function, I got to know two things. I got to know the slope, and I got to know the y-intercept. Okay, and in this particular instance, I don't know either one of those. So what I want to do first is I want to figure out what the slope is. So I'm going to do the formula for slope. So I'm going to do y1 minus y2 over x1 minus x2. And when I do that, I get 3 over negative 3, which is negative 1. So that's going to go here. Now all I have to figure out is what the y-intercept is. So I'm going to go back to y equals mx plus b. I'm going to put this negative 1 in for m. And I'm going to put, I can actually choose either one of these points to put in for x and y. I'm actually going to use this one here just because it has a 0 and it's going to be a little bit easier to work with. So I'm going to put a 0 in for y. I'm going to put a 4 in for x plus b at the end. And when I solve this, I get b equals 4. That goes here. So the equation of this line is going to be y equals negative x plus 4 at the end. So just something that involves linear functions with some things that we've done in the past with slope and y-intercept and slope-intercept form of a line. So now we're going to kind of move into just some special types of linear functions. And this right here is what's known as the constant function. So the constant function, we've been referring to this as a horizontal line. When we're talking about functions, we refer to this as being the constant function. So just remember, when we're talking about the constant function, two things here. One is the slope is 0. And the equation is always going to be y equals some constant c, where c is going to be the point where the graph crosses the y-axis. So that's one special type of linear function. Another is this, and this is what's known as the identity function. The identity function has the equation y equals x. So with the identity function, you have a line where the slope is 1 and the y-intercept is 0. And the identity function always runs through the origin. This point right here. Some other things with the identity function is that if you take a look at some different points on the graph, for instance 1, 1, here you have 2, 2, 0, 0 would be here. So one of the other characteristics of the identity function is that each x coordinate equals the corresponding y coordinate, and the graph is always increasing. So that's just, once again, another special type of linear function that's known as the identity function, and that's going to play a large role in some different things that we'll do moving forward, particularly when we start to talk about some different things involving inverses. And that'll be some things that we'll do in a few weeks here. So moving away from linear functions, we're going to take a look at some different things with some curves. And this is what's called the squaring function. You guys are accustomed to this being a quadratic function, which is a parabola type shape, which is a U shape on the graph. So just some different features of the quadratic function of the parabola. The domain, and this is for the original parabola. This isn't assuming that we do anything with it in terms of changing its shape or where its location is. The domain is the set of all real numbers. Okay, that goes from negative infinity to positive infinity. The range is the set of all non-negative real numbers. So the range for this would be from 0 to positive infinity. The function's even, meaning that it is symmetric to the y-axis, as you can see here. The graph has an intercept at 0, 0, and that's that point right there. The graph is decreasing from negative infinity to 0, so if you look at this piece of the graph here, it's decreasing from negative infinity to 0, and then once it hits 0, it begins to increase, and it increases from 0 to infinity. As we said before, because the function's even, the graph is symmetric with respect to the y-axis, and it has a relative minimum at 0, 0. So this is the point where the graph changes from decreasing to increasing, right here. So remember, that's what a relative minimum represents there. So that is the squaring function. So anytime you have a function whose degree is 2, x squared, you're going to get some type of U-type shape to those kind of functions there. So that's one type of curve that we're going to look at. Another is this. It's called the cubic function. The cubic function, from a shape standpoint, if the x squared function, the quadratic function, is a U shape, we refer to this as a chair shape. You know, sort of, this is the leg sort of part right here, and then here's where you sit, and then here's the back right here. So some different features of the cubic function. One is, once again, the domain is the set of all real numbers. The domain goes from negative infinity to positive infinity. The range is also the set of all real numbers. This also goes from negative infinity to positive infinity. The cubic function is an odd function, meaning that it is symmetric with respect to the origin. So you can see here, this piece, if I were to reflect it over the origin, is the same as this piece here. The graph has an intercept at 0, 0. That's this part right here. The graph is increasing from the interval from negative infinity to positive infinity. So we've talked about this in some other things that we've done in the past involving graphs, but this particular graph here, the cubic function, this piece in the middle here, that is not constant. It looks pretty flat, and what we're basically looking at here is the fact that it doesn't increase at as fast of a rate as this piece does here or this piece does here. So don't fall into the trap of thinking this middle part here is constant. It's not. It's always increasing. And then the other part, obviously, if the graph is odd, then we say that it's symmetric with respect to the origin there. So we already kind of mentioned that. So that is the cubic function. Big thing to remember about the cubic function is the shape of it. It's sort of like a chair shape graph. Another type of curve is the square root function. So the square root function, in terms of its shape, okay, it starts here at 0, 0, and then it has like kind of like a hill shape or an arc type shape. Okay, and it goes towards the positive side of the x and y axis there. So the domain for this is the set of all non-negative real numbers, meaning it goes from 0 to infinity. As you can see here, it goes from 0 to infinity. The range is also the set of all non-negative real numbers. This graph, the range of it is also from 0 to infinity. The graph has an intercept at 0, 0, and the graph is increasing from 0 to infinity, as you can see here. So this graph is increasing as you read it from left to right, from 0 to infinity. And that is the square root function. So then once again, just remember, square root function, you have a graph that's sort of like a hill shape like that there. And then we're going to look at what's known as the reciprocal function. So just notice here with the reciprocal function, you have two pieces of the graph. You have a curve that's down here in quadrant 3, and you have a curve that's up here in quadrant 1. So some different features of the reciprocal function. This is y equals, this is 1 over x. It should say 1 over x up there. The domain of the function, there's two pieces for the domain. There's the piece for this and then the piece for this up top here. So the domain for this piece down here is from negative infinity to 0, and then the domain for this piece up here is from 0 to infinity. The range for the piece right here, this goes from negative infinity to 0, and then for here it goes from 0 to infinity. The function is odd, meaning it's symmetric with respect to the origin, which we're kind of mentioning down here. The graph does not have any intercepts. The graph will not cross either the x-axis or the y-axis. And then finally, the graph is decreasing on the intervals from negative infinity to 0, and it also decreases from 0 to infinity. So a couple things to keep in mind with the reciprocal function, and that is these curves here. If you take a look at this curve down here in quadrant 3, this curve goes infinitely in both directions here. This curve will come very close to crossing the x-axis, but it never actually will. And then when you come down to this part here, this part of the curve will come very close to crossing the y-axis, but never actually will. And then the same thing with this piece up here in quadrant 1. Okay, this piece up here, as it moves up this direction, it will come real close to the y-axis, but will never actually cross it. And then the same thing as we look at it this way, this piece here, this will come real close to the x-axis, but will never actually cross it. So that's what's known as the reciprocal function. So just some different examples here. So for part A, we have y equals 2x plus a half. So one of the things that you want to try to point out when you're looking at the graphs of some different things here is what's the degree, because the degree is ultimately going to give you an idea of what the shape of the graph is. So since the degree for this is 1, this is telling me that this graph right here is going to be a line. So you have the y-intercept here at positive 1/2, so I'm going to just try to get a little point in there. And then I have a slope of 2, which is going to put me up 2 and 1 to the right, which is going to put me here. So I get a line that kind of looks like something like that. So when you're doing this, how do you know if you're right? Well, if I go to my calculator and I go to y equals, and I put in 2x plus a half, then I should get a graph that looks very similar to what we just drew here. So I'm just going to put in here 2x plus 1/2, assume 6, and here's the line that you get, which is very similar to what we drew there. So that's the first part of this. So if I take a look at the next example, which is x squared plus 2x. So this is telling me that I'm going to have a U shape here. So keep in mind that when you're talking about graphing a line, once you know that it's a line, you only need 2 points to graph a line. What I would suggest you do when you're talking about curves is, if you know what the shape is, you can get away with as few as 3 points. Because we know that since this is x squared, this is going to be a U shape here. So some of the things that I would want to do here, I could make an xy table. If I put a 0 in for x here, I'm going to get negative 0 squared plus 2 times 0, right, which I know equals 0. So that's going to give me a point right about here. Then if I'm trying to get some other points on the graph, what I can do is, once again, if we're talking about point plotting, I want to get a point that's on the negative side, I want to get a point that's on the positive side. And I want to see if I can get a u to run through that there. So if I put a 1 in for x, I'm going to have negative 1 squared plus 2 times 1. And when I do that, I get positive 1. So that's one of the points that's going to be on the graph here. And then if I put a negative 1 in for x, so this is going to be negative 1 squared plus 2 times negative 1. And if I substitute that in, this piece right here is going to be negative 1. This is going to be negative 2, so I got a negative 3 there. So I got negative 1, negative 3 is going to go here. So I got 3 points, but I don't know that these 3 points are lining up quite like a U just yet. So let me get a 4th point in here. So I'm going to kind of go on this positive side, maybe get another point, because I'm thinking it might look something like this here as I kind of move through it. So I'm going to put a 2 in for x. And when I do that, I got negative 2 squared plus 2 times 2. And when I do that, this equals 0. So another point on the graph here would be 2, 0. So I get something that looks kind of like that. Now I can kind of see that my graph's going to look maybe something like this here. So let me pull my calculator up just to make sure I'm kind of got the right idea with this. So let me leave this up here just so I can have it to compare. So I'm going to go back to y equals, and I'm going to put in negative x squared plus 2x. And just get a quick idea of what this graph looks like here. So here's the graph. I got the right shape, and it looks like points wise I got the right points there too. So that looks pretty good. So that's just some different things involving the squaring function there. So just kind of moving forward with the next part, part C. This has a degree of 3. So this is telling me that this is going to be a chair shape of some type, right? Degree of 3. So once again, I'm going to start off with an xy table. I'm going to put a 0 in for x here. So when I do that, I got 3 minus 2 times 0 cubed, right, which is going to just be positive 3. So that's going to go 1, 2, 3, 1, 2, 3 up here. Right, so I get a point right about there. Then once again, I'm going to get a point on this side, I'm going to get a point on this side, and see if I can get that chair shape, or that chair looking shape with my 3 points there. So I'm going to put a 1 in next. So this is going to be 3 minus 2 times 1 cubed. Right, and when I do that, I get positive 1. So here's another point, 1, 1 on the graph. And then let me get a point on the negative side. So if I put a negative 1 in for x, and I do 3 minus 2 times negative 1 cubed, right, this is going to be positive 5. So I get another point that's 1, 2, 3, 4, 5 up here. So you can see here I got a little bit of a chair-like shape, and in this case it's going to look something maybe like that. So once again, how do you know if the graph is something reasonably close to what it's supposed to be? So if I leave this up here, I'm going to come back to this, and I'm going to put in 3 minus 2x cubed. And if I graph it, here's what we got. So you can see you kind of have sort of this backwards looking chair type shape for this right here. So that's part C. For part D, I have a square root graph. So that's a hill type shape. So once again, if you recall with the hill that we had here, I had values that I'm going to put in for x. But when I do that, remember we're talking square roots, so I don't want to put any values in for x that are going to be negative, because that's going to get me an imaginary solution. So I want to start with just some positives. So I'm just going to start with 0 first. So I got this, 5 minus 3 times the square root of 0, which is just 5. So one point here is going to be 0, 5. 1, 2, 3, 4, 5 is going to be right about here. So now when I'm putting other numbers in for x, let me sort of pick some numbers for x that I know that when I take the square root of them, they work out evenly. So if I put a 1 in for x, I got this, 5 minus 3 times the square root of 1, which equals 2. So here's another point. 1, 2 is going to go right about here. And then let me get one more point. How about if I put a 4 in for x? Once again, I'm kind of using these numbers because I know that when I put those in for x, they're going to work out evenly inside the square root. So I got 5 minus 3 times the square root of 4. Right, square root of 4 is 2, so I'm really doing here just 5 minus 6, which is negative 1. So I got 4, 1, 2, 3, 4, negative 1 is going to be here. And I'm just going to run my curve through there like that. So once again, how do I know if I got something reasonably close to what I'm looking for here? So if I go to my calculator again and I put in 5 minus 3 times the square root of x, I graph this, there's the graph that we get for that. And then for part E, and this is where for something like part E it's helpful to know what the shape of the graph is. So if I could just take you back real quick to the reciprocal function. So just notice with the reciprocal function I have a curve that's on this side of the y-axis down in quadrant 3, and then I have another one up here on this side which is in quadrant 1. So I have two distinctly different places that these curves are going to occur. So when I go to do this here, I should expect to get some kind of graph that's going to sort of be somewhere in this neighborhood up here and somewhere sort of down in this neighborhood here. So when I go to pick my points for x, I want to make sure that I get enough points in both of those quadrants there so that I get a good representation of what this looks like. So the first thing I'm going to do here is I'm going to put a 0 in for x. So if I put a 0 in for x, I got 1 over 0 minus 2, that's negative 1/2. Negative 1/2. So one of the points is going to be like right about here. Then if I put a 1 in for x, so I got 1 over 1 minus 2. So that's negative 1. So another point's going to be 1, negative 1, which will be right about here. And then if I put, let's say, a 3 in for x, just notice I don't want to put a 2 in for x here, because if I put a 2 in for x, that's going to make the function undefined. So I don't want to do that there. So if I put a 3 in for x, this is 1 over 3 minus 2, which would be positive 1 there. So I got 1, 2, 3, positive 1. That's going to go here. And then if I put, so I'm kind of getting this point that's up here, I think this point's going to sort of speak to this part of the graph that's up here, and I think these two are going to speak to this part of the graph that's down here. So maybe let me get another different number in for x here. Maybe let me put, to kind of deal with this part down here, let me put maybe like a negative 1 in for x. And when I do that, I get 1 over negative 1 minus 2, which is negative 1/3, which is going to be maybe like, I don't know, right about, this one's going to be tough, right about there. So for this bottom piece here, I'm going to get a curve that maybe looks something like that. And then for this top portion here, I'm going to put some other numbers in for x. So I already got a 3 in for x, and that's this point here. So if I were to put, let's say, a 4 in for x, so if I did 1 over 4 minus 2, right, that's positive 1/2. So I got positive 4, positive 1/2, that's going to be right about here. And then if I put a 5 in for x, this is going to be 1 over 5 minus 2, which would also be positive 1/3. And that's going to be even closer to the x-axis there. So when I do that, I'm going to get something that kind of looks like that there. So how do I know if I'm right when I do this? Well, let me leave this up because I want to show you one quick thing about this after we talk about the calculator. So if I go to y equals, and I'm going to go to alpha f1, so I can get my fraction up here. So this is going to be 1 over x minus 2. And I graph this. So here's the curve that's sort of in the bottom left. There's the curve that's in the top right. So one of the things to notice about this, okay, is that this graph, I'm going to come back to my original here and let me maybe do some erasing so I can clean up some of this. Nope, I don't want to erase the whole thing. I just want to take out that, but I guess it's not going to let me. So in any event, when I take a look at my graph here, so one of the things to notice is that these two curves are never going to cross the x-axis. We talked about that from the original reciprocal function. But also notice with this that neither one of these curves are going to cross this vertical line right here, x equals 2. And the reason for that is because if I were to take this 2 and substitute it in for x here, that's going to make the function undefined. So 2 is not a part of the domain. And that's why neither one of these curves is ever going to cross this line right here. Because if I were to substitute a 2 in for x into the equation here, that's going to make the function undefined. So just something to keep in mind when we're talking about graphs and doing some different things with reciprocal functions. So one of the things that we're going to look at next are some other types of graphs and functions. We're going to look at what's called a step function, sometimes what's referred to as the greatest integer function, and then we're also going to take a look at a piecewise function, which we've done some different things with when we were talking about functional notation, but now we're going to get into actually looking at how to graph something that involves the piecewise function.